The lapel of the, is this, yeah, we're good. Okay, awesome. Thanks for coming out. So yeah, this talk is called radBIOS. It's basically about how I YOLO'd together an audio thing. So this is like the inevitable, like, who I am slide. I do some Rust stuff. I work on security for Stripe. I'm gonna see how many times I can make him do that. I've done a bunch of things in the past, but like most of it has been software engineering, just like solving different problem with software. I'm going to apologize now. I managed to get conpox like before even getting to Vegas, and so if I wander off topic or I say things that aren't making any sense, please feel free to like interrupt me because my head feels like it's full of cotton wool. Anyway, so radBIOS. This talk is not about like groundbreaking research in like audio encoding or manipulating data. It's much more about how like despite knowing nothing about this, I managed to get it to work. And specifically, I managed to get it to work while like actually decomposing all of the parts in it, such that I can now like talk reasonably confidently about audio things like exfiltrating data. And so the backstory is a couple of years ago, Dragos found these like malware samples for this thing he was calling radBIOS. He was positively convinced it was nation-state malware. The media lost their collective shit and made things like this. But so he made a bunch of like fairly plausible sounding claims about it. But there was a lot of controversy because like he wouldn't cover up the samples, and then he did, and the samples weren't real, and they sent him hardware, and anyway, it was a long story, and there was a bunch of stuff about it. But so in the middle of this whole debacle, my good pal Snare starts tweeting these. And so in case it's not clear, that is a BIOS chip on the face of someone doing something radical. And so I was drinking with Dominic and Mike at ShmooCon last year, and they planted this like horrible idea in my head to build a thing that looked and behaved a little bit like badBIOS and call it radBIOS, and then come and talk to some jerks about it. This talk is very explicitly not about badBIOS, and like don't ask me about it afterwards. I kind of like, I'm not a malware reverse engineer, and like I don't even want to have opinions about whether, I mean, it's one of those things that like, until there's concrete evidence is kind of pointless to debate. So anyway, this is like this is like the bulk of Dragos' claims about like what badBIOS actually did. So it was able to exfiltrate data via audio. Specifically, they were going after either key material or documentation. It was able to infect other hosts with audio, which was the claim that caused everyone to kind of like hiccup and do a spit take. It was completely platform agnostic, so it didn't care whether you're on a Mac or a Windows machine, or you had like Phoenix BIOS or some other manufacturer, or you had UEFI, as well as like it didn't care what platform you're running on top of. It was like file system agnostic. And finally, it ran entirely inside of UEFI, or at least as far as like launching an infector to target your host machine, which is a series of bold claims. Like each one independently is kind of a solid effort. But so these were the two things that I kind of like looked at and thought, I can probably do this. At the end of the day, if I actually found like UEFI bugs that I could infect people with audio, I would not use it to exfiltrate data. I would use it to infect people with, anyway, it's not important. So, cool, fucking rad, right? So I'm actually going to do this talk in the most bizarre order possible. I'm going to do the demo now because the demo runs during my entire talk. And then hopefully at the end, I will have successfully moved an SSH key from that machine to this machine using nothing but audio. I will preface this by saying, if anyone has a dog or just really doesn't like high-pitched noises, or if anyone in this room doesn't want to have a bit of a headache by the end, like, probably mention it now. I gave this talk in Hamburg one time, and a guy that I work with is literally bleeding from the face by the end. I'm like almost totally convinced that it wasn't my fault, but it's kind of hard to say with actual certainty. So now we do some live hacking, and this will go well like it always does. So I actually have a shell on my demo laptop, which is, I'm not planning to exfiltrate it over, did my shell die? So that'd be super neat. Sorry, 1 second. Live demos, am I right? So I have an SSH shell to it. Obviously I'm not planning on actually exfiltrating the data with it, because that would be kind of shit. Because trying to swap cables between two machines is miserable. As is trying to type like this.
You got mail.
I do have mail. Come on, you can do it. I believe in you. This is not the failure mode I was expecting for this talk. This is what I get. I decided to use my phone tethering instead of the con Wi-Fi because I figured that had a much better chance of not screwing me. Aha! Okay. So, sweet. I actually had the fonts too big for once. Okay, so what I'm going to do is, so it sits on top of this platform called Ground Station. I have this script called slurp. And so slurp, you just give it a file, and it adds it to the local database of like stuff that you want exfiltrated. So I'm going to run this on an SSH key. I seriously considered using ed25519 keys, because they're like this long, and it'd be crazy easy. But I was in a good mood, so I did it with an RSA key, which is actually like fairly sizable. And so now on this laptop, the one that I'm presenting on, I'm going to run the server, which is called Sound Station, for fun, punny reasons I'll get to in a second. So this is going to start listening on these 3 frequencies, and then on this one, whoop, if I remember how to computer. Okay, so this machine is now like broadcasting. That's new. I fucking love live demos. Woo! Okay, so what's happening here? Neat. So 2 people independently said that they were going to fuck with my demo, and I'm starting to wonder if that's the case. Alright, hang on. This will either start working, or I will do some, like, spectacular bullshit to try and make it run. Anyway. 1 second. I swear I've done this before. Alright, fuck this. Yeah. Should be in... Get fucked, Liam.
Set baseball for the 4.
Woo! Live demos! Anyway, so... Oh fuck, now I'm catching that exception. Oh, fuck's sake. No, I probably have some Python I care about. No, this is the pit, isn't it? Oh god. Okay. So... Oh, is my connection... Fuck's sake, really? This... I swear to God. Alright, just take my word for it. I'm starting it on this computer. It's not over SSH. It's doing a thing. It doesn't matter now because I caught the exception. Right. Let's get back to the talk. As I'm going to drive into, it has this like unique property of fault tolerance in that even if it falls over 1,000 times, if it works even once, it'll work. Let's just see what's going to happen. Anyway, it's not important. Demos suck. So, as you probably gathered, I built it on top of this thing I wrote a while ago called Ground Station. And so Ground Station is a distributed graph database. Everything in it is content addressable, which is kind of neat, kind of has some like awkward API constraints. But the interesting thing about it is that when I originally wrote it, my goal for the project was that if you take 2 machines near one another, they will automatically like share all of their state. And then if you take those 2 machines and take them to 2 more machines, you're going to have this like graph explosion, but what you wind up with is a bunch of like shared information amongst everyone who's ever interacted with the graph. And so it's almost entirely written in Python, has very few external dependencies, and kind of conveniently, at this late stage in the game, I deliberately built it in a really modular fashion because I wanted it to be possible to kind of extend it with, like, new types of data to put into it, and more specifically, like, more, transport protocols, like audio, it turned out later. So anyway, when I first wrote it, I literally was just screwing around with the idea I had for, a decentralized network. I kind of, in spite of the fact that I get a little bit mad every time anyone says decentralized, because it's nearly always not actually the thing that they want, I thought I wanted a decentralized thing. I also explicitly wrote it because the company I worked for migrated to Jira, and it's a piece of shit. So I I replicated Jira into ground station, and then I wrote a thing so that everyone in the office, if their ground station nodes were near each other, it would like sync up the Jira database. I did all of this to avoid interacting with Jira. And honestly, I recommend the experience. So anyway, it does a couple of other kind of neat things out of the box. One of them is that I mentioned it was content addressable, and the reason for that is the object database I'm using at the very lowest level is actually Git. So one cool property of it is that if you point it at a Git repo and then bring it near someone else, it syncs Git repos, which turns out to be really cool if you have like 200 software engineers, for example. Anyway, it has a shiny web face. I used to have it in this talk. I took it out because it was sort of meaningless and a waste of time. But so ground station has kind of three core components. It has an object graph, it has protocol drivers, and it has transport drivers. I'm going to talk a little bit about the first two because it kind of doesn't make sense without them, but obviously like the main reason we're here is transport. So like under the hood, it's a graph database. And so what that means is you have nodes and edges, and the edges are basically like a property of the nodes. And everything in it is immutable. So the only operation you can do on the graph is to insert more data. And I mean, this sounds limiting, but it turns out there's a lot you can do. For example, if you want to update a node, you just like push a node in that has a reference to the one you're superseding, and you just put the new data in that. So what this winds up looking like, yeah, I'm fucking awesome at Keynote art. So anyway, this is like a really, a very, very simple graph. And the only operation you can do is like put more stuff in it, right? And so as you're adding things, each node has a reference to its like logical parent, and that's how you traverse the graph. You start at the top and you just like keep walking parents until you get to a thing without parents. But this has this cool property that if you lose data, or you never got it in the first place because you were using a janky audio transmission mechanism or whatever, the parts of the graph that aren't actually orphaned by that missing node are still traversable and complete. Which means that for a lot of use cases, if you suspect that you're only going to have a fraction, you can still like reason about it meaningfully. And so, just kind of like to try and recap so it hopefully makes a bunch of sense. So this is the source of truth, which is like the object whose name you would like refer to talk about this whole graph. And this guy is like the root, which is, the most immutable thing because there's really nothing you can do about it now. So anyway, that's like an overview of a graph database. As far as protocol drivers go, they're really just this like thin layer around the Git ODB. Basically so that, they have some notion of what your underlying data is actually meant to look like. They handle, doing things like presenting the data to the user as well as like taking data from the user and like munging it into a format that ground station can understand. There are actually a bunch of these now. The happiest moment of my life was when somebody who wasn't me contributed one to ground station, which I was not expecting. But so like Git is actually technically a protocol driver, I guess. But someone wrote like a message board, and so you like post on the message and you take your laptop for a walk. When you get home, it has new posts in it, and they're all from nerds who do this. It's not good. It's not important. But so this is the protocol driver I just interacted with, that you hopefully just saw. And this is like a really thin example. Like all it knows how to do is read an arbitrary file, shove it into the database, and then when you eventually run a transport driver, it can exfiltrate it to somewhere else. So like, we're finally getting on towards like actually talking about transport. The first transport protocol I wrote was kind of naive, although it wound up scaling far further than I expected. So the assumption was that all of the nodes are on like a homogeneous link layer network. So you can at least like reach other peers, and your broadcast traffic will like find its way to someone. And so what I did was I set every node up to just like shriek UDP broadcast traffic indiscriminately. And if any of the other nodes like heard it, that had enough addressing information that they could negotiate a connection, they connect, sync up, and do this like hilariously complex handshake that I devised for like optimal syncing of the graph database. And then eventually like both parties now have all the data. Hooray! Like, what does this actually have to do with hopping air gaps? I couldn't find an actual bunny hop photo, but he's like so close. So first of all, I'm going to preempt Q&A every single time I've done this talk, which is why didn't I use sound modem, which is this thing in the Linux kernel, which kind of natively tries to do this, or GNU Radio, or whatever. There's another thing like anyway. So there are a bunch of projects that sort of do this. They're very black boxy, they're almost entirely inscrutable. Sound modem turns out to just not work very well as being Linux specific, which kind of defeated my works everywhere I go. GNU Radio, I'm pretty sure no one really understands except whoever wrote it. And like dollar thing, I don't know, no one told me about it. But I mean, the crux of this was specifically that I was coming into this knowing basically nothing about audio except that like I'd seen a sine wave before. And like, I wanted, at the end of this, to be able to, like, at least, like, ask reasonable questions, even if I didn't have all the answers. So, I found this thing called QuietNet, which was actually the thing that I got at Shmoo by. This chick, Kate Murphy, I actually ran into her a couple of years ago at B-Sides Toronto, and we hung out for like 2 hours before we put together that she was the one who wrote QuietNet, and I was the one who did radBIOS, which was like an exciting coincidence. But so anyway, QuietNet is basically this send-receive protocol that runs on two machines. It like sends data from one to the other, but it's like almost entirely written in very scrutable Python. The only third-party dependencies it has is PyAudio for actually like driving the sound hardware, like taking your array of samples and actually like shoving them out of the speaker, and NumPy, because it turns out that like math is fairly expensive if you do it in userland Python, and we'll be doing some math. So this is an example of a QuietNet session, and I would love to say that I like had to try really hard to get it to fail in this way. Unfortunately, it's just like fairly unreliable. But for like very defendable reasons, like if you're using this in its kind of intended purpose, which is like, I type things into my computer and they show up on your computer. I mean, like, reading this, you still know that I was trying to say hi there, or something close to that anyway. And so the reason that this corruption very specifically happens is that it uses an encoding called PSK31. And so I've obviously like trimmed this a little bit, but looking at it, you can very quickly see a couple of things. One is that there's no repeated zeros in the middle of any of these code words. The reason for that is that it separates code words with 2 zeros as a sigil, and so it would be impossible to tell the difference between them. The other is that it's like very obviously optimized for English text. The shortest message is a space, and the second shortest is an E. So from the ground up, it was very deliberately designed only for migrating like text that looks a fair bit like English around. At one point, one of my very early prototypes actually base64 encoded binary data and then transferred it with the don't do that. Anyway, so yeah, it has some nice properties though. Particularly, one of the things I ran into a lot is like, how do I synchronize the two streams? Like, how do I get the two computers to agree on where in this like stream of arbitrary data we are? And it turns out that a sigilling scheme that doesn't rely on like fixed length words and constant sync is really, really convenient. You just like drop into the stream, and then the first time you see 2 zeros, you're at the start of a word, and then you just like keep reading. Awesome. Right, so I like took QuietNet, and I like hacked onto 2 scripts until I could like very reliably move like a kilobyte of data overnight. And then I started thinking, well, there's probably a better way. I might actually have to go in a bit deeper than this. No one's going to be terribly interested in this. And so I asked myself, how even to audio? And this is kind of what I came up with. And this isn't like a perfect pipeline, but like in the general case, you'll probably find yourself doing something that looks almost exactly like this. So at the very top, you like reach out to your audio hardware and you say, hello, I would like a stream of frames. And it's possible that PyAudio segfaults, but if it doesn't, you get a stream of frames, and it's awesome. So then, once you have your stream of frames, you like take some frames and you do a thing called a fast Fourier transform, which turns your frames into points. And at that point, your points now represent like how much activity there was in a given frequency at that time. And then you take your points and you walk along them like with a sliding window saying like, hey, at what time was there this tone that I'm very specifically interested in? And that gives you bits. Finally, once you have your bits, you can, in my case, I ham the shit out of them, which I will also get to try and turn them into symbols, and finally you turn the symbols into bytes, and then you have data. So simple. Why didn't I just do this in the sorry? Alright, I'm going mad. I swear alright, anyway. So, Fourier transform. I figured I'd skip over the, like, give me frames thing, because it's, like, you import PyAudio and say, give me frames. So a Fourier transform, this is like the Wikipedia definition. It transforms a signal from its original domain, which in our case is time, into the frequency domain, which, I mean, I sort of get it now, having done this for a while, but like, the actual thing that it lets you do is ask the question, was this tone present in this set of samples? And like, programmatically, it kind of manifests as just this big array of floats. So this is the like Fourier transform GIF. Like, sort of helped me understand it a little bit, I guess. So this is transforming the wave into like an array of floats, and then it'll play again, and you. My clicker. This is literally the first time I've used it. And so if you do it again, you transform back from whatever domain you're in back into the domain of time, right? And so it's what is it? Transitive is the mathematical property for this. Anyway. It's not super important. The important thing is that you FFT the shit out of your frames, and you get a bunch of points, right? And so this is what your points look like after you extract the intensity of a given tone. And so once you have your points, you can start walking along them and saying, like, what is the average intensity over this window? Right? And so, like, as you slide along them, for, like, this set, it might make sense to use, like, 3 as your threshold. This gives you a modicum of hysteresis protection, as well as just protecting you from people in the audience making hideous noises. Actually, so that was the other thing I forgot to mention, is that at least one joker was lurking with an air horn this morning. So you all might be getting air horned, as well as a headache. So anyway, you, like, slide along your window of frequencies, and you transform them into bits. And so, like, now you have an array of bits. And so, like, the naive idea would be to say, well, like, if the tone is there, it's a 1, and if it's not there, it's a 0. Like, that's sort of how binary data works. And this works okay if you know for a fact that you're in a stream, and you have some way of, like, independently synchronizing the stream with the other end. Otherwise, like, your peer having written bad Python or whatever and crashed, is just going to transform your stream into, like, megabytes of zeros, which is almost certainly not really the thing that you want. And so I fiddled with this for a while, and I wrote some really, really janky stuff that sort of worked in the lab, and then I called it a day, and then 2 days later I was like, okay, this is not okay, I should do something more professional. But so the reason I actually got noticed like this in the first place was a talk that Mike Osman and Dominic Spill gave at ShmooCon 14. I'm going to try and avoid digging into it too deep, because it turns out you can talk for almost exactly an hour about it comfortably. But the notion is that you have linearly isolated Hamming codes. And so this is an example of a Hamming code. You can flip any bit in this message and unambiguously work out which message it was actually meant to be. Which is really good, right? Like, if your data might get flipped on the wire, you can, like, take it and unpack it. You obviously, like, you pay some overhead in, like, how much data you can transfer. Like, I have to send 6 bits to transfer, like, 2, which is not great, but whatever. But so the interesting thing about their codes are nothing new. The interesting thing about their research was that they split this into 2 subcodes, right? And so if you flip, like, any 2 bits in this message, you can still unambiguously work out that it didn't belong to this set. And so the reason they built it was a defense against the packet-in-packet attack that Travis Goodspeed developed, wherein you basically just, like, send valid wireless frames in IP payloads, and the first time something bit flips, it, like, reads on until it finds a valid-looking header, and then it's like, great, header data, I love header data, and you get to inject packets into a network that you're not privileged on. And so their proposal was that we encode header data with one subcode and payload data with another subcode, such that even if it gets bit flipped, you can still tell that, like, you ought not parse this payload as a header, because that'll probably end badly. And so this is kind of like an example of what this actually looks like in practice. Like, I flip this bit at the end here, and you basically just, like, look at edit distance. Most people do this with lookup tables. Another early prototype of this. So after they gave the talk, this guy opened a pull request saying, like, hey, your C++ program that runs for, like, 3 days to generate these codes is neat and all, but Z3, which is a satisfiability solver, can do it in, like, 9 seconds. And it was, like, so fast that I just, like, took the Z3 implementation, which happily has Python bindings, and literally put it in my thing and invoked a sat solver for every single packet. Which turned out not to be optimal. You can just generate lookup tables. But so I still, like, I was on the fringe of knowing things about DSP at this point. I'd processed some signals in my time, but I still like, didn't really know what was going on. But I kind of looked at this thing and I was like, wait, let me get this straight. I can get bits wrong and they'll still be right? Amazing. It's going to be impossible with that. So I literally just started trying to belt nails in with this, like, amazing hammer. And so this is what one of my first attempts looked like. You might be able to see where I'm going with this. So you remember my PSK31 slide where it was like, you can't put interior zeros. I just stretched everything. I just made it all way longer. Because it turns out, like, the bigger something is, the easier it is to find. This actually did work. One time I did this, it moved 240 bytes in 45 minutes. Which, like, I agree, is fuck all. Don't want to do that. However, like, one of my first demos that I spoke about earlier moved a kilobyte overnight. And so, like, sweet, I nearly picked up an order of magnitude. Apples. Still useless, but, you know, I took exactly the same process, and to be fair, the method of picking these ones was incredibly scientific. I wrote a program to just run it over and over, and add ones until it successfully got the same data. I call it YOLO science. So anyway, this is like what that actually looked like on the wire. This is just some like protocol analyzer app for my phone. It looks like Morse. Someone in Q&A will probably point out that I should have used Morse. Technically, they're right at this point. The data rate would have been significantly better. But so like, you know, I had all these like janky mechanisms for moving data across an air gap, but I didn't really solve the problem of like doing it reliably or interpreting the data afterwards or like doing it in a not lab condition where I'm sitting there and I can very carefully press return on both machines at exactly the same time because they're kind of hinging on this assumption that they're synced up. But at the same time, it sort of worked in the lab. So I was like, must be close now. As I mentioned earlier, Ground Station's first implementation had this like two-step or make a bunch of UDP noise and then establish a TCP connection with the other end. Anyone who's dealt with TCP knows that it's like sort of noisy on the wire. But I was like, well, like connecting from one machine to the other and like sending some data with audio isn't crazy hard. It sort of works. Like just doing it in the other direction in like a synchronized and coherent fashion ought not to be too hard. I can just write a BSD socket interface and like TCP sockets and it'll be awesome. And like all I had to do was change all the constants from like import socket to like import audio whatever and like just call it socket thing and I don't have to change any code. A+. So that doesn't work. Audio is really hard. Duplex is crazy difficult, as I discovered. One thing yelling and me making a bunch of noise like I am at the moment is like reasonably straightforward, but two things, just trying to negotiate what they're even going to listen on when they don't know anything about each other is a nightmare. And so I kind of like, I fiddled with this for a while. I actually like, I had a bunch of reasonable stabs at it, right? Like, I really wanted this duplex thing to work. And as it turned out, I sort of wanted it to work for bad and stupid reasons. But like, the thing that I wasted the most time on was reinventing wheels. Like, the best part is that at no point did it occur to me to just like read the TCP spec to like see exactly what it does. Like, but so this was my first attempt where I wanted to have this like, TCP-like thing where you like send a packet and then your other end acts it. If you're paying very close attention, you'll realize that like a TCP payload is gigantic and a TCP ACK is tiny, but in this instance I'm doing it bitwise, so that didn't work very well. In as far as, I mean, like it sort of worked, but my data rate went back to the like kilobytes in days sort of order. And so like this didn't get me anywhere, but then I kind of figured, well, like, what if we take the retransmit approach? Like instead of actually waiting for an explicit ACK, what if I announce myself and then wait for my, like, I make the announcement tone every like 5 seconds or so. And when my peer hears it, they just start making a bunch of noise on like some random frequency. And I just keep an eye on the spectrum. And the thing that like gets really loud after I announce is like, probably the thing that I'm interested in. So awesome. I'll like start listening on that. And then the second I have their thing, I will start barking. And then we've like sort of negotiated a frequency. Maybe it'll work. It was really difficult to optimize for. I also did some pro YOLO science. Every single time I've given this talk where I like lurk around the room, I'm going to give it in and try different frequencies till the transmit rate is good. So anyway, I kind of tried this thing, and then instead of trying to ACK individual payloads, like everything in Ground Station is request driven. Like there are no informational messages. The only time that you talk to the network is if you want someone to do something. So I thought like, great, I'll just like keep sending messages until I get a valid response to them. And that way I avoid like needing explicit ACKs. I just like wait until someone like definitionally has got it because they responded to it. This also doesn't work. But so I kind of went back to the drawing board and started to think about like why I actually wanted duplex communications. The reason that I implemented them in the first place in Ground Station was because I was syncing gigantic databases. Like some of the Git repos that it operates on have like gigabytes of data because sometimes a designer checks in a Photoshop file and that's the end of the goodness of your Git repo. But like in this instance, there was like never going to be a case where these databases were like big. I mean, if they're that big and you're trying to move it around with audio, like I think you just need to look at your life and your choices. But it also had a couple of like the duplex thing actually broke some things that I kind of thought were neat when I was first thinking about this. So one example is that like as it stands, like this machine is making noise and kind of because I'm doing a demo, like I'm targeting this one, but actually like anyone in the audience could like run get this random SSH key. One of the things I've been sort of playing with in the last few days, because it only just occurred to me, was actually just recording it on my phone and then like playing it back later instead of trying to like pause it in real time. But so like, yeah, my duplex thing was like complex and error prone, and my favorite, a complete monstrosity to debug, because like I didn't even know what frequencies it was going to pick, and I could log them, but I was often recording the wrong thing, and the handshake took forever because when you're transmitting like order of bits a second, as it was at that point, there's a lot of sitting. So I started like, I went back to the drawing board and thought like, how can I make this work without doing this really hard work, which is difficult? And I went back to thinking about like the way my graph works. So earlier I mentioned that the graph I'm using has this property of content addressability, which if you're not familiar with it, ordinarily like when you think of a database, you think of a thing that like probably has some like identifier payload pairs, right? And you can go to the database and say, hey, I have this ID, I want the data associated with it, give it to me. And you get to pick both of them. In a content addressable database, the name is always a digest of the. And so what this means is you get given data without any like a priori knowledge of what it's meant to be called, and you hash it, and then you just shove it into the database, like with that name. And so when you're encoding this, you actually stick the parents inside of the body as, an array of names of parents. And in this way, like, the entire message is kind of like self-contained in that if you flip any data, it'll actually hash wonky, and it won't wind up there, right? So like, in this instance, I couldn't work out exactly how to try and describe this, but like, so this guy here, like, has the hash of its parent stored inside of its body, and this one got corrupted on the wire, like a bit flipped or whatever, but that made it hash entirely differently, and it kind of like lands outside the graph conceptually. Which means that if you just like keep trying, all of the fucked up packets will just like not land in the way, and then when you traverse down from here, like you will only hit the good path. So I was like, okay, cool. Like instead of trying to be really, really clever and like optimize for always getting the data and only transmitting data that my peer needs and like doing all this smart stuff, what if I just like yell incessantly all of the data that I have and just kind of like assume that my peer will hang around for long enough to like probabilistically get it all? Which like, again, like it has some neat property. I mean, one, it works, which is great. But it also means that like you can actually have like essentially a data fountain, and like going near it means that you'll get a set of the data. And if you come back the next day, you'll get some more, and so forth. So anyway, I cranked the hamming way back because unfortunately, like with consistency comes just like more data that you need to transmit. And I went really overboard with the like just add more bits solution to all of my problems. So I wound the hamming way back to the point where like transmitting messages was feasible again. Started like yelling, I chunked up the payloads really aggressively, started yelling them and just putting everything into the database, whether or not it necessarily looked okay or not. And this actually sort of worked. And so I went into this hill climbing mode where I was like, okay, I feel pretty good about my mechanism for moving the data around, but like, I feel pretty good about my mechanism for encoding the data, but like, my faux file layer that I've kind of YOLO'd together is kind of bullshit. Like, what else can I do? So I decided to actually read a paper. And I had sort of valid reasons for not doing this first instance. The biggest one was that, for sort of like dumb reasons, I was really, really interested in actually kind of like deliberately not invented hearing the whole thing, like building it from the ground up as much as possible, because I figured it's like extremely difficult to build, like not impossible, but very, very difficult to build something for yourself that you still don't understand. But so I kind of like, I figured I'd roughly reached the limit of what I could achieve, like inventing my own signal processing algorithms. So I started doing a little bit of reading, especially I started actually reading up on things that I'd like heard of, but the math looked really daunting in the first place. So, unambiguous encapsulation protects me from bit flips in the sense that if I have like a well-formed message and it's a bit wonky, I can like fix it. But it doesn't help me at all when I have this like long stream of bits that is like, orders of magnitude bigger than an individual message, and I'm like, great, like, where does the message start? And at various points I tried, this like wonky windowing thing where you like slide along it and then you see like, at what point do you have the most valid messages, and like that's probably the correct offset. But it had huge problems, and it meant that like, if you drop a bit in the middle, you like have to go back, you have to keep trying this. And it was like a lot of work, and I just kind of didn't care for it. Like, I kind of got the feeling that someone had done this in a way that was less janky than that. So I went back to like what I was actually doing to key the data on the air. What I've been doing so far is called frequency shift keying, right? You basically like make a tone on a frequency whenever you want to send a bit. And like, as long as you've agreed on what the frequency is in the encoding scheme, like you can transmit data. Great. And And so I'd read a lot about phase shift keying, which is like unambiguously, get it, the correct thing that I wanted. Like that is what I wanted to do. But I read a bunch of papers, and specifically I read some implementations of it, which are difficult to find in native Python, which was kind of like, I just didn't want a C++ monstrosity. But I got to the point where I fundamentally agreed with the author that it worked, but it was still like mostly unclear to me why. Like, you take the signal and then you delay it and then you multiply it by itself and the signal just like comes out. And yeah, so I kind of looked at it and I decided that it was going to be easier to build a smarter FSK than it was to actually like wrap my head around PSK. So I kind of went back to the drawing board and looked at like the way my FSK worked. And so as it stood, I like had a single bit of information, which is like, is this tone on or off? And I was encoding bits into that by saying like, with my one bit, which was kind of unpleasant for a variety of reasons. So I kind of looked at it and I'm like, well, I have this like entire spectrum to play with, and I'm using this one arbitrary frequency that worked pretty well in a conference room once. Like, I can probably do something smarter there. And so what I did was I separated out into 3 frequencies, right? So I have 19K, which is the headachiest one I've found so far, which denotes a 1. 17K, which denotes a sigil, which is basically like, this is the gap between 2 messages. And 18K, which is a 0. And so once you take your stream of data and do your FFT on it again, you wind up with something that looks like this. So this is just a tuple of floats that I was printing, and it basically shows like how prevalent each of these 3 frequencies are at any time. And so this is before I kicked off the listener, or sorry, before I kicked off the, I think I called it a shrieker in the code base because I thought it was funny. And so this is like basically what background noise happens to look like in my hotel room last night. But then once you start it, all of a sudden you get these like gigantic values, and it's like, great, there's a signal. And so one of the interesting things is that, because of both like my technique, my poor choice of frequencies, and the fact that I'm not kind of doing any post-processing to clean up the signal, they all jump up. Like in this instance, like the 3rd column, which I think is the 0 bit in this case, is like intuitive. I mean, like eyeballing numbers, you can say this is probably it. But like all pretty high as well. And so like one of the first things I was doing was just like looking at what's above a threshold got me nowhere. I had to actually take the data, FFT it, find out if anything was above the threshold, and then like do the sliding window dance again to see like which one was consistently above the threshold. So anyway, I was like, I did this and I got like another order of magnitude improvement on my bit rate, as well as like much better accuracy. Like the Hamming wasn't needing to soak up quite as many things, but like my Hamming code Rube Goldberg machine was still doing a hell of a lot of work. And I like kind of looked at that as like the next thing that I could plausibly optimize. And so this actually came up when I was talking to Osman at Shmoo this year, because I filled him in on all the stupid shit I'd done in the year since he gave me a bad idea. That like, this is kind of like how I was hamming these bits before, right? Like I take the bits and I feed them in. But in many instances, like, I mean, this medium is analog and the way I'm interacting with it is naive. It's pretty common that like I have indeterminate bits, and like traditional signal processing kind of like, well, so it turns out there are 2 schools of thought on this. This is all Osman telling me that I'm an idiot. So I smugly was like, I invented a thing. So typically when you're processing signals, at some point you have to make the choice between hard decisions and soft decisions. And what that boils down to is like, how early in the pipeline do you take your array of floats and turn it into like concrete bits? And I took the 3rd door because I didn't know there were only 2. So what I did was like, when I had bits that I just like wasn't sure about, like it really could just go either way, I just like stored a 3rd value. And I let the Hamming code soak that up because it meant, if I resolved all the bits that I was pretty sure about, and then resolved the bits that are actually like guaranteed to be wonky, I wound up recovering a lot more data. And the process for doing this is pretty easy. You try both of them, and whichever one has a closer edit distance to a valid word is almost certainly the thing. So anyway, does anyone have a headache? No one? Amazing. Is anyone bleeding? Okay, so I have a hunch that this is going to not be working. Just quietly. Alright, well, that's definitely failed.
Very loud.
It is very loud. So the reason for that is actually honestly a little unclear to me. I used to do the clicking. So the clicking isn't the thing that it's listening for. The clicking is like, so if you imagine that you have like a waveform that like looks like this, when you start a speaker, you want to like kind of like ease into it basically. Like, you want to, like... Yeah, exactly. And that's what it is. It's basically every time I light up the speaker, it pops.
At what point do you start the process? I would hear the high pitch drone, or like before you start your presentation.
I mean, that wasn't me if it started beforehand. I would totally, so more than one person didn't even threaten, just flat out told me they were going to. So like, yeah, I would actually believe that. In any case, I'm officially, like, evidently I wrapped the wrong thing in try accept. So I'm just going to write this off as a failure. I'm sorry, guys. This is the first time the demo has failed.
Can you write it to go at like something audible, like 600 hertz?
Yeah, I mean, I can. Oh, fuck. Let's just do this again. Really? Oh, need it. Crashed. Awesome. Love segfault. Anyway, so I can make this stop. I don't. This is sort of pointed at me, and my head really hurts now. I'm gonna regret doing this in a second. Because I don't have another SSH key handy, so I'm gonna use my real one. Actually, no, I'm not gonna do that. So let's do. Neat. Okay, so I wrote an object into the database. So this is where. That's an A. I did music once. Great. How loud is my volume? All right. So. So this is what it actually winds up sounding like on the wire. Yeah, it actually is. Does anyone here watch Rick and Morty?
Yeah.
It is definitely human music. Anyway, so I know what to tell you. In theory, I could have pulled that apart. Sorry? Yeah. Anyway. Fuck, I should totally do that. Like, I mean, like, I did, like, learn some stuff from doing this, make some conclusions. I mean, like, the first one, which probably goes without saying, is this is a really stupid way to steal things from spies. You actually, like, maybe should use this for a research project. I kind of, like, from the ground up, all of the components that I built in this are deliberately really sort of reusable. So, like, if you're building something with this, or even, like, toying with the idea, or you just, like, you're in, like, fuck you, you're an idiot, I can do this better mode, which you probably can, shoot me an email about it. I would love to, like, chat about it and see if we can work together or something. Audio isn't as inscrutable as I kind of felt like it was when I picked this up, although, to be clear, it's still, like, pretty inscrutable. I spent so much time shotgun debugging with the signal analyzer on my phone, and the best part, it doesn't have a zoom thing, so I had to, like, take screenshots and then, like, yeah, it's not great. So, fun fact, do you guys want to see baud lines? No, it's not, baud line is broken on my computer and it makes me angry. But like the hill climbing approach to this actually turned out to be much more reasonable than I was expecting it to be. So when I picked up this project, like, especially the first few weeks were just like misery and sadness because like nothing worked ever. All computers were bad. And so I kind of like, I got the sense that this was going to be a very binary thing, right? Like it either like works flawlessly or it doesn't work at all. But like, once I got over that hop of like actually getting data off the wire, you know, doing something with it and it having at least like something to do with the original data, even if it's not bit for bit identical. Once I got to that point, like the optimizing for local maxima in like some specific field and then like picking the next thing that seems like a bottleneck, actually worked a lot better than I was expecting it to. And if you do this, you will so get used to coding with a headache. One time I flew from Melbourne to New York and worked on this on the plane. So I have sound cancelling headphones. Yeah, it was miserable. It also turns out that a plane is an acoustically shitty environment for this kind of thing. And then I have to do the inevitable like greets thing. Ultimately, I would probably never have done this research if if Snare didn't tweet a bunch of stuff about radBIOS. Michael Osman for being really, really gentle with my feelings when he told me that everything I'd done ever had been invented years ago. Mike and Dominic for doing exactly the same thing, but they weren't gentle with my feelings. Kate Murphy, QuietNet, which I borrowed a lot of both code and ideas from. And finally, so I went to CanSec this year, and I met Dragos, and I was half expecting him to glass me, and he didn't do that for taking the piss out of him for an entire year. So that was pretty neat. And yeah, this is Ground Station is up. So I did a bunch of work on this in the last couple of weeks, and I didn't want to release it before the talk. It's not Sweet O Day, but I was like, yeah, whatever, I'll publish it after the thing. So I'll push that today. QuietNet is up there, and you can play with it, as well as sound mode and GNU Radio if you want inscrutable things, or you're smarter than I am and you can work GNU Radio. Cool. I guess I have some time for questions. Does anyone have any?
So have you thought about doing amplitude shifting?
Yeah. So it was another one of those things that I kind of looked at. So I actually forgot to put it in my slides now I mention it. I probably have content for the next 10 minutes. So one of the things that I actually wanted to do was to do 6 FSK. So my ham encodes are all 6 bits wide, and so I could completely eliminate the where in the stream problem I am if I can send all 6 bits at once. The problem that I had was that as I mentioned earlier, the frequencies all bleed over into each other, and that's really not a problem when I only care about the strongest one. The strongest one is probably the thing that I was trying to send. But with all 6 bits, all of a sudden I actually need to care about the individual values of all of them, and so the bleed over just obliterated all of my data. I got the sense from the reading that I did that ASK was going to have similar kind of problems, in the sense that there was just fancy post-processing that I didn't do before it'd be meaningful. That's not to say it can't or won't work, but that's kind of why I didn't go too far down that road. To be honest, I kind of I got to the point where I was making real ground with FSK, and particularly FSK is really, really easy to debug. You just look for the hot patches on the spectrograph. So that's why I kind of just persisted with it. Yep.
Yeah, for that, getting late,
Yeah, so I kind of I intuitively knew that numbers that are multiples of each other is probably a terrible idea. It was a little unclear to what extent I had to go overboard, and I picked some random numbers and they worked, and I was A+. So the other trick with that was I was using shitty laptop speakers and mics, and when I was trying the 6FSK thing, I kind of had the sense that if I could spread the frequencies out far enough, I'd get away with it. The problem being that there is actually not very much usable spectrum between the audible band and the point at which these speakers are just not capable of materially producing noise anymore. And so that really limited my options, again, if I was trying to do the naive thing, which I kind of consistently was.
Where was that band?
So I think, from memory, the human audible band kind of ends at order 14K or something. There are a bunch of audio people in the room who probably want to correct me. Yeah. Sorry, 15 to 20. Yeah. And so these machines I mean, to be clear, it's a little unclear if the problem is the speaker or the mic, but anything above 20K was just a complete write-off. It was basically impossible to recover data. Sorry.
How crappy a speaker is private?
So I didn't go too crazy with that. I tried it on a bunch of laptops, basically any laptop that someone would let me execute arbitrary code on. I had a stab at it. Results were pretty similar. I mean, I was a little bit surprised. I'm not an audiophile per se, but I really like music, and so I have a reasonably nice set of on my desk. And so I tried this with them because I was maybe they'll be good. But I mean, it turns out that studio monitors are kind of really aggressively optimized for the audible spectrum, because giving people headaches really delicately is not super important to their business model, I guess. I guess at the end of the day, the takeaway I had on what speakers I'm using is that everything I'm doing is sort of naive and sledgehammery enough that it didn't really matter. I fiddled for a little while because I was curious to know if I could actually fingerprint a machine based on its audio signature, because I thought that'd be kind of cool. I got as far as yep, that's a computer. Wasn't as signalful as I was kind of hoping.
Talk about stacking data in
Yeah, so I mean, that's cropped up a bunch of times. A lot of people have told me that I need to jam this into dubstep because no one will ever know. To some extent, it's kind of like, I mean, it depends exactly what your plan is as far as stegging it. The way I've implemented this, it's like fairly tolerant to background noise. I mean, excepting this one Bloodbath demo, it has very reliably worked in a lot of rooms, like while I'm talking and answering questions and whatever in the past. I think, particularly the way that I'm doing it, like you would almost certainly need to do something kind of fancier, like PSK, where you treat the music as being like a carrier wave, and then you modulate that, with the data. I mean, like doing what I'm doing by just like lowering the frequency so it like happens to be in the music. I don't think it'd work. I mean, basically all of these things are like, it is definitely possible. Like whether or not it's within my reach or it's something that I could make work in the next couple of weeks reliably is like probably not.
Here's an experiment.
Sorry. So the question was I tempted to implement, what was it, V32? Yeah, so kind of. So I read there's also a Linux module called AX25, which is another one. I don't know. So I cut a bunch of irrelevant stuff from this talk, but there is a project called Byzantium, which is trying to build distributed mesh networking, which was actually the people that contributed the other module to Ground Station, because they wanted, their use case very briefly is like, you're in a disaster-affected area, like, all of the infrastructure is destroyed, but everyone still has laptops. It'd be nice to be able to talk to each other. And so they built a message board on top of it so that like, I put a post in the message board being like, my goats have escaped. And someone else puts a post in the message board to be like, whose goats are these? And then someone who knows both of us happens to like ferry between us both. And the graphs sync up and like now I know who has my goats. And so they got a contract from, or a bounty or like a grant from some organization to try and make their thing work over ham radio. And so I worked with them on the original like AX25 implementation. And so that was one of the things that I picked up and I was like, this will be easy. It turns out that like, once you're on the other side of a ham radio, like, your signal is already so much better attenuated than like audible noise in a janky room with echoes and misery. My sense is that they're not, like, even if you implemented it, it would still kind of only get you as far as the like protocol decoding phase. Like, I don't think it would have helped me very much as far as actually like pulling signal off the wire in the first place. But I could definitely be wrong. Okay, I'm nearly out of time. I've got time for like one more, or 3 minutes. I have time for 3 more. But there are no more questions. Amazing. Awesome. Thank you for having me. Sorry.